So I wanted to spend my last screencast for week 15 on, I guess, some reflections I had, both as I have been teaching this stuff in my class, and I'm currently on potential, just finishing up potential and going into circuits, and also just kind of talk about some questions I had as I sort of reviewed this material and reviewed the course that we went through. Um, so to be honest, I was really unsure of myself with electricity. I'd go through the equations and I'd have kind of a piecemeal um, teaching strategy, I guess, for the students. Sort of teaching the units of electrostatic charge as a disconnect between potential, and then that also as a separate unit, sort of from circuits. But this course really helps to provide a unifying theory to connect all those different ideas. Um, and there's still definitely some questions, but I feel more comfortable with the conceptual understanding of all of these ideas and how they relate. And so that's great because I think that's the foundation of successful understanding and successful use of problem solving and use of mathematical equations to solve problems. Knowing which equation to use and how to go about thinking about what the answer means. So I guess one question I had is so as I was teaching potential, my textbook shows this equation for potential for fields due to point charges. So these are the potential at various locations around point charges, as this equation here is negative kq over r. And that's all fine and good, except that sign, I'm still not understanding why this is a negative sign. I talked to my colleague about it, and he didn't understand that either. My textbook didn't have any negative sign there. Here with the gravitational potential analogy or corresponding equation, this negative here, I guess this suggests that as a potential decreases, or as r decreases, the distance between my two objects decreases, then my potential would decrease. Because as my r would get smaller, I would get a larger negative value for potential. And so that suggests that, your energy per mass would decrease as you get closer, as the two masses get closer to each other, such as I get closer to the Earth. There's less potential energy there per unit kilogram. Okay, that's fine, because again, it would be a larger negative number near the Earth's surface for potential, suggesting lower potential energy per kilogram. But that analogy that thinking doesn't seem to work here for the corresponding electric potential equation. Because if I have a positive charge, a positive central charge, so this Q would be positive, and I was close to that central charge, R would be small, and that would give me a large negative number for potential. Saying again, if I use the same kind of thinking as for gravitational potential, that my large negative electric potential suggests that it's a very small amount of energy per charge. Close to this positive central charge. But again, if I'm thinking about, a positive test charge, it takes a lot of work to move that close to the positive central charge. Therefore, I would think that there would be a high amount of energy per charge closer to the central charge. And then also, if we think of this central charge as being negative, so I have a large negative central charge, that means my potential near the central charge would be a large positive. And again, suggesting that it'd be a high amount of energy per charge if or close to the negative central charge. And that it doesn't make sense if I'm thinking about this positive test charge in space. A positive test charge close to a negative charge, that would be a low amount of energy. So I don't know why this calculation seems to result in a high potential and thus a high amount of energy per charge. And so that thinking just eludes me, and I haven't been able to get around that. So what I've done is taken away the negative here. And so if that is the thinking, if I do that, then I do find that, for around close to a positive central charge, there would be a high amount of potential. And that seems to make sense because, as we did this electric field mapping, near a positive charge, you get high potential. And then as you move away, you get lower potential. And I understand that around a negative central charge, it's a negative potential. And as you move away, you get less negative. So maybe that sign just reflects, whether or not it's around a positive or a negative charge. Anyway, so that's a question there. I thought it was nice to go through some equation, some mathematical analysis, and combine the Coulomb's law with this equation for field strength, electric force per charge, and resulting in this equation here. The electric field strength equals KQ over R squared is a way to quantify your electric field strength in units of newtons per coulomb. So it was a good application of algebra, and I think my students, that's more from a mathematical modeling perspective, but that is a wonderful way, to use algebra and try to sort of, develop your own equations. And the modeling method, again, is also wonderful, and there's lots of applications here to develop mathematical models through data collection and graphing, and then finding slopes of lines, linearizing data, and then coming up with equations. But here it's just kind of a straight up, using algebra to combine two equations to come up with another equation. So I think that's rich. I'm not sure how my students necessarily appreciate that, but I think that is good sort of work for them in terms of reasoning. So let's see. I'm currently on potential, just finishing it up, and we did some of the electric field mapping where we used the conductive paper, and we entered points into the electric field mapping template, and then came up with a three-dimensional graph. That was honestly a bit tedious for my students. Really, we just did map the electric field around 2 point charges, either 2 positive point charges or 2 positive and a negative. But that took a while to develop that three-dimensional graph. And I'm thinking that maybe at this point of the year, it might be better just to go with the method of looking at potential differences with the three-dimensional modeling technique that